Okay, so this is a calculus course, so let's take a look at an example. I'll call it example 1, and this one will involve a little bit of calculus. Let's take a look at the following set of parametric equations. X equals 4 minus t squared, and y is equal to t squared plus 4t. Let's analyze the meaning of some of the things that we're used to doing in calculus. Well, one of the things I could do is I could take the derivative of x, but I have to take it with respect to t. So the derivative of x with respect to t looks just like negative 2t. And similarly, I can take the derivative of y with respect to t, which in this case is just 2t plus 4. So what do these quantities mean? Dx dt is pretty much how I'm moving in the x direction with respect to time. So you can view this as the change or the velocity for you more physics-minded students in the x direction. So horizontally, how is it moving? Okay, and you can think of y, dy dt, as the change or the velocity in the y direction. Okay, so let's plug in some numbers and actually try to interpret that. So what if I want to know what dx dt is at time equal to 1? So if I plug that in, I get negative 2. So that tells me that my particle or graph is moving to the left because it's going negative 2 in the x direction. Dy dt at the same time, at time equal 1, if you plug it in, you will get 2. So in this situation, my velocity in the y direction is positive, so I'm going up. You can represent this as a vector if you're the physics type. We'll say v of 1, and the vector is negative 2, comma 2. Which tells me I'm moving left and up. Or, if you prefer using unit vectors, negative 2i hat plus 2j hat. Okay, we might also want to ask, what does it mean when dx dt is equal to 0? That's something that we've been dealing with in Calc A, so what does that mean? So this just means there's no change horizontally, or you can think of it as no horizontal movement. So if you're a particle and you are not allowed to move at a given instant in time horizontally, that tells me that you are purely moving up and down. So when dx dt equals 0, you actually have a vertical tangent, only moving up and down. If dy dt equals to 0, then you're not moving in the y direction. You're not allowed to move up and down, so you can only move left to right. So there's no vertical movement. So that tells me you have actually a horizontal tangent. Okay, so we can actually figure it out for the equation we have above, because dx dt, which is negative 2t, that is equal to 0 only at time equal to 0. And similarly, dy dt, which is 2t plus 4, that's only 0 if t is equal to negative 2. Okay? So keep that in mind, and we're going to go ahead and graph it on the graphing calculator. Okay, here's the graph of the function. It turns out it's not the full graph. If we want to look at a better part of the graph, we should maybe start a little bit earlier. So I'm going to start my window actually at from t equal negative 3. So if I go to my window and I change my t min to negative 3, I'll get a little bit better look at it. If I do a trace on this, I can actually choose different values of t. So if I choose t equal to negative 2, notice I end up right here, and if you look carefully, that spot will actually have a horizontal tangent. And we know that's the case because the work we did, we knew dy dt was equal to 0 when t equals negative 2. Now let's look at t equals 0 and show that it in fact has a vertical tangent. So if I do a trace, and I trace it to t equals 0, you can see right here the coordinates is 4, 0, and the graph is going straight up and down. And you can also draw arrows along that direction. So just to kind of sketch a general graph for what this looks like, okay, just based on what we saw earlier, it looks something like this. Okay, and the direction was in this direction. And this point right here occurred at t equals 0, which when you plug in was 4 comma 0. And this point down here, which should be horizontal, occurs at t equal negative 2, which if you plug in negative 2, you can get your coordinates as well. But the question is, how do we find not dx dt and dy dt, but how do we find dy dx? Isn't that what we've been interested in all along? Or how do you find the slope, in other words, of the tangent line at a point? Well, the way we get dy dx is we'll actually take dy dt and we'll divide it by dx dt. It's pretty simple, but something kind of surprising happens. If we look at our current example, okay, so dy dx is just going to be equal to, students make a lot of mistakes of which one to put first. It's dy dt on top, so 2t plus 4, and then dx dt on the bottom over negative 2t. What's kind of weird about this is a function of time. Usually, when we find dy dx, we get y as a function of x. So what that means is if I want to calculate, for example, if I want to know the slope, or dy dx, at a specific location on the graph, let's say I want to know where it is at 3 comma 5, I would actually need to figure out what time that occurs at. Okay, so how do I figure out what time that occurs at? Well, I will just set x equal to 3 and y equal to 5. So 3 is equal to 4 minus t squared, and 5 is equal to t squared plus 4t. And you can solve for the times where that occurs. You have to, however, find the times where they match, because, for example, here I get 2 times, which is t is equal to plus or minus 1. If you solve over here, I will also get 2 times. I will get t equals 1 and negative 5. So the only times that match is 1. So over here, what time are we evaluating this derivative? It's at t equal to 1. Meaning I just plug it in, so 2 times 1 plus 4 over negative 2 times 1, that will give me my slope at t equal to 1, which works out to be negative 3. So at t equals to 1, the graph should be having a downhill slope, and we can check t equal to 1, if I do a trace, is here, and you can see that slope looks downhill, and it pretty much, you could estimate it's about negative 3. Let's do a second example using calculus, and what we're going to do instead of just finding the derivative is we're actually going to find the equation of the tangent line at a specific point, 6 comma 8, for the following parametric equations, where x is equal to t squared plus t, and y is equal to t cubed. Okay, double check that these points are on there, but you can pretty much figure that out. So the first thing we should do is figure out what times these occur. So when x is equal to 6, what times does that occur? So 6 is equal to t squared plus t, which you can solve by moving the 6 over. T squared plus t minus 6 equals 0. And by factoring, you can show that t equals negative 3 or 2. And similarly here, y is equal to 8. So 8 equals t cubed. And you can get that t is equal to 2. So 2 is the ones they're going to have in common. The next thing I would have to do is to find the slope. So I need to find dy dx. But keep in mind, dy dx is just dy dt over dx dt. So dy dt in this situation is 3t squared. Dx dt in this situation is 2t plus 1. And these are being evaluated at t equals to 2. At t equals to 2, your slope will be 12 over 5. Okay? So using point slope equation, y minus y1, so y minus 8 is equal to m, which is 12 over 5, the slope, x minus x1, which is x minus 6. And that is the equation of your tangent line at 6 comma 8. One last thought is, how do we find the second derivative? Okay, how do we find that? Well, let's think about it carefully a little bit. Let's kind of view the second derivative as really being written in this form. Okay, so now some students will say, well, why don't we just take the derivative of the first derivative, dy dx? Keep in mind, however, that dy dx is a function of time in parametric equations. It's a function of t. So I can't take the derivative with respect to x. I have to take the derivative with respect to t. However, this will not get me the left-hand side. Okay, and so I need to multiply by something, which is really using the chain rule in order to get the second derivative with respect to x. With a little bit of thought, you can show that if I multiply by dt over dx, then I will end up with exactly the same thing, which is the second derivative of y with respect to x. Okay, in essence, these dt's cross out. Okay, so as a formula, if you want to find the second derivative of y with respect to x, you actually take the derivative with respect to time of dy dx and then divide by the green, which is, if you look at it, dx dt. Okay, so it's a little bit strange, but I'll leave that for you on the homework to work out.